Hello student, welcome back. We are going to start today's session. It is Lecture 4, Module-3, Microcontroller and Embedded System. Sangita Roy, Assistant Professor, Electronics and Communication Engineering Department, Danula Institute of Technology. So in the previous class we have started in the Module 3, that 8051 Assembly Language Programming Tools. In that classes we have already completed some basic ideas, how it is formed and different syntax instructions, what is assembly language programming, what is high level language programming, why it is necessary in assembly language programming, structure, opcode operand mnemonics, few instructions, move instruction, jump, so we are going to this session with lecture 4, how to calculate exact time delay in 8051 microcontroller. The delay subroutine consists of two parts, setting a counter and creating a loop. Example 3. Let's find the size of the delay if the crystal frequency of 11.0592 MHz is connected. Move A #55H. Again, move PI, A call delay, CPLA, S jump again, time delay, then delay, move R3 #225, here DJNZ R3 here, then return. Answer is, we have the following machine cycles for each time delay subroutine. Move R2 #255, machine cycle 1. DJNZ R2 here, machine cycle 2. Return, machine cycle 1. So here the time delay is equal to 255 into 2 plus 1 plus 1 into 1.085 microsecond, because this cycle will complete it 255 times, so it will take into 2 up to DNZ, then one machine cycle for the return and one machine cycle for the instruction move R2 #255. So this is the total time delay it requires. Very often we used to calculate the time delay based on the instruction inside the loop and ignore the cycles associated with the instruction outside the loop. NOP upon instruction. NOP instruction is used to increase the delay in the loop. NOP means no operation, simply waste time. Loop inside a loop, delay. This means is used to get a large delay, that is to is used a loop inside a loop, which is also called a nested loop. Example 4. Let's find the time delay for the following subroutine with 11.0592 MHz crystal frequency is connected to the 8051 system. Delay, move R2 #255, machine cycle 1. Here NOP, machine cycle 1, NOP, machine cycle 1, NOP, machine cycle 1, NOP 1, DJNZ R2 here, machine cycle 2, return. So it will consist of 255 into 1 plus 1 plus 1 plus 2 into 1.085 microsecond, that is to 166.0.05 microsecond. The time delay of the two instructions outside the loop is 1660.05 microsecond plus 1. It is for move R2 hash 255 and return. That is to total of 1803.32425 microsecond. Example 5. For a crystal frequency of 11.0592 MHz, let's find the time delay in the following subroutine. The machine cycle is 1.085 microsecond. Delay. Move R2 hash 200 machine cycle 1. Again move R3 hash 250 machine cycle 1. Here NOP machine cycle 1, NOP machine cycle 1, DJNZ R3 here machine cycle 2, DJNZ R2 again machine cycle 2, return machine cycle 1, and it is calculated as previous 1 plus 1 plus 2, so 1 plus 1 plus 2 into 250, that is to 1085 microsecond, and there is two outside instruction, that is 1 plus 2 into 200 into 1 plus 1085, that is to 651 microsecond, that is to total of 200 into 1085 microsecond, that is to 217000 microsecond plus 651 microsecond for the initial two instruction. IO port programming in 8051. Upon completion of this chapter, you will be able to explain the purpose of each pin of 8051 microcontroller, list of the 4 ports of the 8051, describe the dual role of port 0 in providing both data and addresses, code assembly language to use the ports for input and output, explain the use of port 3 for interrupt signal, code 8051 instruction for IO handling, code bit manipulation instruction in the 8051. So this is the pin diagram of 8051. I am not going to detail because we have already done. The 8051 family members come in packages such as PDIP dual in package, QFD quad flat package, and LLC leadless chip carriers. All packages have 40 pins that are dedicated for various functions such as IO, read, write, address, data, and interrupts. 20-pin version of 8051 also provided by some companies with a reduced number of IO ports. The above pin diagram consists of 40 pins. The total of 32 pins are set aside for the purpose of 4 ports P0, P1, P2, P3. Each port has 8 pins. The rest pins are designed as VCC ground, XTL1, XT crystal oscillators, reset, EA enable. These pins must be connected in order for the system to work smoothly. And VCC for supply voltage, it is plus 5 volt. Ground is 20, pin number 20. It is DC ground. XTL1, XTAL2. These are two on-chip oscillator but requires an external clock to run this. The quartz crystal oscillator connected to XTL1 and L2 needs two capacitors of 30 picofarad value. On side of each capacitor is connected to the ground. The maximum oscillator frequency connected to this XTL1 and XTL2 is referred to as the speed of the 8051. There are various crystal oscillator available used to connect XTL1 and L2, that is 12 MHz, 20 MHz, 11.0592 MHz, etc. The 12 MHz chip must be connected to a crystal with 12 MHz frequency or less. 20 MHz microcontroller requires a crystal frequency of no more than 20 MHz. When the 8051 is connected to a crystal oscillator and is powered up, the frequency on the XTL1 2 pin using the oscilloscope can be observed. Reset value of some 8051 register. Program counter PC reset value 0, accumulator 0, register B 0, program status word PSW 0, stack pointer 7, data pointer 0, DPTR. Reset is the pin 9. This is an input pin and is active high. When a high pulse is applied to this pin, the microcontroller will reset and terminate all activities. This is called power on reset. All values given in the above table register will be lost upon power on reset. The value of the program counter is 0 upon reset, forcing the CPU to fetch the first opcode from ROM memory location 0000. This means that we must place the first line of source code in ROM location 0 because that is where the CPU wakes up and expects to find the first instruction. The two-way of connecting the RST pin to the power on reset circuitry is diagram below. The reset input must have a minimum duration of 2 machine cycles in order to make the reset input effective. The high pulse must be high for a minimum of 2 machine cycles before it is allowed to go low. EA, external access. The EA pin is connected to VCC for the 8051 family member. EA pin is pin 31. This pin must be connected to either VCC or ground. EA pin cannot be left unconnected in case of 8031 and 8032 microcontrollers. This pin is connected to ground. In 8031 and 8032 family members, there is no on-chip ROM. Code is stored on an external ROM. Connected to EA pin to ground indicates that the code is stored externally. PSEN, Program Store Enable. PSEN is a output pin. This pin number of this pin is 29. It is an 8031 based system where an external ROM holds the program code. This pin is connected to OE, output enable pin of the ROM. ALE, address latch enable. This is an active high output pin. This pin number is 30. When connecting to an 8051 to an external memory, port 0 provides both address and data. The 8031 multiplexer address and data port are port 0 to save pins. The ALE pin is used for demultiplexing the address and data by connecting to the G pin of the 74LS373 chip. Function of the input-output of I/O port pins. There are 4 ports, P0, P1, P2, P3. Each port has 8 pins. The port 0, 8 pin names P01, P01, P02, P03, 4.5, 6 and 7. All the ports upon reset are ready to be configured or used as an output. To use all these ports and input port, it must be programmed. Port 0. Port 0 had 8 pins, that is to P 0.0, 0.1 to 0.7. Pin 39, 38, 37, 36, 35, 34, 33, 32 accordingly connected. This port can be used for input or output. Each pin of the port 0 must be connected externally to a 10K ohm pull-up resistor to use port 0 as both input or output ports. This is because the port 0 PO is an open drain. This is not the case in case of P1, P2 and P3. It is open drain in terms of used for MOS chips and open collector is used for TTL chips. To use port 0 for both input and output, we have to connect port 0 to pull-up resistors. When external pull-up resistor connected, upon reset, port 0 is configured an output port. Role of port 0 as an input port. To make port 0 as input port, the pull-up resistor are connected to port 0. The port 0 must be programmed by writing 1 to all the bits. Let's examine the code example below, which the port 0 is configured first as an input port by writing 1s to it when the data is received from the port 0 and sent to port 1 P1. So move A #0FH, load accumulator with the value FFH in hex or 255 in decimal. Move PO A, make port 0 as an input port by writing all wants to eat. Back, move A, comma P0, get data from port 0. Move P1, comma A, send it to port 1. S jump back, keep doing it repeatedly. The dual role of port 0. Port 0 can be used to configure for both data and address. The port 0 is also designed as 80 to 87 when connected and 8051 to an external memory. Port 0 provides both address and data. The 8051 multiplexer address and data through port 0 to save pins. Address latch enable ALE indicates if port 0 has address or data. When ALE equal to 0, it provides data D0 to D7. But when ALE is equal to 1, it has address A0 to A7. With the help of 74LS373 latch, ALE is used for demultiplexing address and data. Port 1. Port 1 has a total of 8 pins, P1.02, P1.1, P1.2, P1.3, P1.4, P1.5, 1.6 and 1.7. Port 1 can be used as input or output. As compared to port 0, this port does not need any pull-up resistor. Port 1 already has internally connected pull-up resistor. Port 1 is configured as an output port when reset. Example 1. Let's examine the code which will continuously send output to port 1, the alternating values of 55H to and AAH. Move A 55H, back move P1A, A call delay, CPLA, SJMP back. Role of port 1 as input port. Port 1 must be programmed by writing ones to all the bits in order to make port 1 as an input port. Example 2. Move A #0 FFH, load accumulator with FFH in hex. Move P1A, make P1 as an input port by writing all ones to port 1. Move A, P1, get data from port 1. Move R3A, save data in register R3A called delay wait. Move A, P1, get another data from port 1. Move R4A, save data in register R4, A called delay wait. Move A, P1, get another data from port 1. Move R5, A, save data in register R5. In example #2 above, the port 1 is configured as an input port by writing ones to it. Then data is received from that port and saved in R3, R4 and R5. Port 2. Port 2 also has total of 8 pins. Port 2.0, 0.1, 2, 3, 4, 5, 6 and port 2.7. Port 2 can be used for input or output port. To make port 2 as an input, the port 2 must be programmed by writing ones to all bits. Example 3. Move A #55H, back move P2 equal P2, A call delay, call A SJMP back. In example 3 above, the code will send out continuously to port 2 an alternating value 55H and AAH to toggle the bits to port 2 continuously. The role of port 2 as an input port. The port 2 must be programmed by writing ones to all the port 2 bits to make port 2 as an input port. Example 4. Move A #0 FFH, load accumulator with value 0 FFH in hex. Move P2, A, make port 2 as an input port by writing ones to all the bits of port 2. Back move A, P2, get data from port 2. Move P1, A, send data to port 1, SJMP back, keep doing it repeatedly. In example 4, the port 2 is configured as an input port by writing all ones, then the data is received from the port and it's sent to port 1 continuously. The dual role of port 2. The port 2 has dual role. Port 2 is assigned as A8 to A15. This indicates that port 2 has dual function. Microcontroller is capable of accessing 64K bytes of external memory. It needs a path for 16-bit to address. P0 provides the lower 8 bits via A0 to A7, while port 2 provides A18 to A8 to A15 address. When 8051 is connected to external memory, port 2 is used for upper 8 bit of the 16-bit address and is connected to be used for input or output operation. Port 3. Port 3 has total pin of 8, that is to port P3.0 to P3.7. Pin 0, pin 10, 11, 12, 13, 14, 15, 16, 17 is assigned accordingly. Port 3 can be used as an input port or output port. Port 3 does not need any pull-up register, just like port 1 and port 2. Port 2 does not require any pull-up register. Only port 0 requires pull-up register. Port 3 has additional function of providing signals of interrupts.